Hello and welcome to Chapter 8, where we will discuss our home base Earth as a planet. After this chapter, you will understand Earth's interior, magnetic field, plate tectonics, internal and external forces on Earth, and Earth's atmosphere and weather. We will begin this chapter with 8.1, the global perspective. As discussed previously, Earth is a medium-sized terrestrial planet made primarily of heavy metals. We are the only planet in the habitable zone of our solar system, where the temperature is not too high or too low to support life. Here we can see the famous image known as the blue marble. This is an image of Earth from space taken on one of the Apollo missions. Inside of Earth is more difficult to study than you may think. We have only had direct contact within a few kilometers into Earth's crust. We actually know less about deeper than 5 kilometers into Earth's crust than we do about Venus's surface. However, we do have ways to determine indirectly what Earth's interior is made of. One way to indirectly figure out Earth's composition inside is to study seismic waves. These are waves caused by earthquakes or explosion. Waves travel differently through different medium. Therefore, we can determine the medium the wave has passed through by looking at the wave itself. By looking at different waves, at different locations, we have been able to determine the layers of Earth's interior. Here we can see a depiction of the different layers of Earth: the crust, the mantle, and the inner and outer core. We will first discuss the crust. There are two different kinds of crust: oceanic and continental. About 55% of the crust is oceanic crust. It is about 6 kilometers thick and made of basalt, a volcanic rock. The other 45% is continental crust, some of which is also beneath the ocean water. This crust is 20 to 70 kilometers thick and made of granite. Crust is the easiest layer to study, but makes up only 0.3% of Earth's mass. Here we can see a depiction of Earth's crust. The darker the color, the deeper the crust in that region extends. The blue represents water and the other colors represent land. Next, we have the mantle. It starts where the crust ends and continues for 2,900 more kilometers. The mantle is more or less solid, but the temperature allows for some very slow flowing and deforming. It is more dense than our crust because of the pressure. We have samples from the mantle from volcanic eruptions. Next, we have the core. There is a solid and liquid core. The core has a diameter of 7,000 kilometers, which is bigger than the entire planet of Mercury. The solid core has a diameter of about 2,400 kilometers. The core is incredibly dense because of all of the pressure. This separation into layers like the crust, mantle, and core is evidence of differentiation. At one point, Earth was hot enough that the heavier metals were able to sink to the core and the lighter metals stayed above them. Next, we will discuss Earth's magnetic field. Magnetic fields are caused by moving charges or currents. The metals in Earth's liquid core carries charges and circulates, which creates a current. This generates a magnetic field which looks as if there was a giant bar magnet in Earth aligned almost with the poles. This field extends into space and can trap charged particles. The region where this can happen is called the magnetosphere. Here we can see a depiction of Earth's magnetic field. The charged particles it can trap come from solar wind. Solar wind also extends our magnetic field in the direction not facing the sun by a significant amount. We will now discuss in more detail Earth's crust. Earth's crust is composed of oceanic basalt and continental granite. These are both igneous rocks. Igneous rocks are rocks that have cooled from a molten state. On Earth, there are two other types of rocks not found on other planets: sedimentary and metamorphic. Sedimentary rocks are fragments of igneous rocks or the shells of living organisms deposited by wind or water and cemented together without any melting. Metamorphic rocks, on the other hand, are produced when high temperature or pressure alters igneous rocks or sedimentary rocks physically or chemically. Metamorphic rocks are produced on Earth because of geological activity carrying the surface rocks down to considerable depths and then bringing them back up to the surface. Without such activity, these changed rocks would not exist at the surface. There is another type of rock important to planetary studies: primitive rock. Primitive rock no longer exists on Earth, but we can see it in smaller objects which crash into Earth. Primitive rock has largely escaped chemical modification by heating. Primitive rock represents the original material out of which planetary system was made. No primitive material is left on Earth because the entire planet was heated early in its history. To find primitive rock, we must look to smaller objects such as comets, asteroids, and small planetary moons. We can sometimes see primitive rock in samples that fall to Earth from these smaller objects. Here we can see an example of igneous rock. Lava flows and then cools into igneous rock. Now that we've discussed the composition of our crust, we are going to discuss plate tectonics. Plate tectonics is a theory which explains why the continents are moving. The process of convection, where heat escapes from the interior to the upper mantle, causes continental drift. The upper mantle and crust is divided into about a dozen pieces like a jigsaw puzzle, and some are drifting away and others toward each other. This happens because of hotter material rising and cooler material sinking in the mantle. This process of convection occurs on other planets and stars as well. Here we can see a photo of this division of the upper mantle and crust. We call each section a plate. These plates move a couple of centimeters a year. When these plates interact, they create four types of interactions: pulling apart, one plate burrowing under another, sliding alongside each other, and then jamming together. The theory of continental drift is credited to Alfred Wegener. He theorized this because of a discovery that, with slight adjustments, the continents could fit together. You may know this massive continent as Pangaea. Wegener's theory was heavily criticized and not widely accepted because he did not describe the mechanism which could cause the continents to move. He died before his theory would become accepted. This is an example of pioneers in science being heavily criticized and ostracized by the general public and scientific community of their time. However, Wegener's hypothesis is now the centerpiece of our view of our dynamic Earth. His theory is essential in our understanding of astronomy, and he is now acknowledged as a pioneer of astronomy. We will now discuss plate interactions. When plates pull apart, they cause rifts, most occurring in the ocean. This allows magma to flow to the surface and harden into new crust like you can see in the first picture. The old crust now has to go somewhere. This happens when one plate burrows underneath the other, creating a subduction zone like you can see in the second picture. Thinner plates are thrust down into the upper mantle and are often marked on the surface by an ocean trench. Some plates run parallel to one another. However, they do not slide smoothly. They will slip up against one another, causing earthquakes. The longer between slips, the larger the earthquake, since there is more time for stress to build up between the two plates. Where the plates run parallel to one another is called a fault. Many mountains have been formed due to plates colliding with each other. This burrows one plate and raises the other to kilometers above the Earth's surface. This creates mountains. Mountains have sharp peaks, however, this is not due to the forces which created them. The sharp peaks come from erosion of water and ice. Volcanoes, on the other hand, are places where magma is allowed to rise to the surface of Earth. Mid-ocean ridges, like we discussed, are an example of volcanoes. Volcanoes often occur along plate interactions, but volcanoes can also occur at hotspots far from interactions. These hotspots are places where heat is allowed to rise from the interior of Earth. Now that we've discussed Earth's surface, we are going to talk about Earth's atmosphere. Our atmosphere exerts a pressure of 1 bar on us. This is equivalent to 1 kilo per square centimeter. We have evolved to be accustomed to this pressure, so a change making it much greater or smaller causes us to not function very well. The entire mass of the atmosphere sounds like a lot, 5 times 10 to the 8th kilograms. However, if you compare the atmosphere to the entire mass of Earth, it is of less percentage of the mass than comparing a single hair on your head to your entire mass. We are going to discuss the structure of our atmosphere. The troposphere is the lowest part of the atmosphere. It extends 10 kilometers above Earth and is where airplanes fly and our clouds exist. Convection of warm air heated by the surface and the cool air from higher up occurs. Above this troposphere is the cloudless stratosphere. This is 50 kilometers above the surface and contains a layer of ozone. Ozone is a type of molecule which protects us from the UV radiation, and the layer adds heat to our atmosphere. Once we reach 100 kilometers above the surface, the atmosphere is very thin. Satellites can orbit with little friction, and light molecules occasionally can escape Earth's gravitational field. This is called atmosphere leakage. Here we can see the layers and section of our atmospheres. Important aspects of our atmosphere are weather and climate. Weather describes the atmosphere's response to changing inputs of energy from the sun. Climate describes changes which last decades and centuries. Here we can see an example of weather. This hurricane developed because of a combination of the tilt of Earth's axis, which causes moderately quick rotation, and oceans of liquid water. Some of the best examples of a change in climate were the ice ages. These ice ages were primarily the result of changes in the tilt of Earth's rotational axis, produced by the gravitational effects of other planets. Our next section discusses life on Earth, chemical evolution, and climate change. Evidence of the first living being has been erased by our ever-changing crust. However, we can see that the oldest surviving rocks, from 3.9 billion years ago, show evidence that life had already existed when they were formed. At 3.5 billion years ago, life had achieved the sophistication to build large colonies called stromatolites, a form so successful that stromatolites still grow on Earth today. Here we can see a fossil which contains stromatolites. Genetic analysis tools have allowed scientists to construct what we call the tree of life, which we can see here. This figure shows that life on Earth is dominated by microscopic creatures that you've probably never heard of. Note that the plant and animal kingdom are just two little branches on the far right. Most of the diversity of life and most of our evolution has taken place at the microbial level. Indeed, it may surprise you to know that there are more microbes in a bucket of soil than there are stars in the galaxy. Since the energy for making new plant material from the chemical building blocks comes from sunlight, we call the process photosynthesis. Studies of the chemistry of ancient rocks show that the Earth's atmosphere lacked abundant free oxygen until about 2 billion years ago, despite the presence of plants releasing oxygen by photosynthesis. Slowly, however, the increasing evolutionary sophistication of life led to a growth in the plant population and thus increased oxygen production. The presence of oxygen, and hence ozone, thus allowed colonization of the land. It also made possible a tremendous proliferation of animals, which lived by taking in and using the organic materials produced by plants as their own energy source. As animals evolved in an environment increasingly rich in oxygen, they were able to develop techniques for breathing oxygen directly from the atmosphere. On a planetary scale, one of the consequences of life has been a decrease in atmospheric carbon dioxide. In the absence of life, Earth would probably have an atmosphere dominated by CO2, like Mars or Venus. Carbon dioxide, or CO2, plays a key role in retaining the sun's heat in our atmosphere by a process called the greenhouse effect. CO2 acts like a blanket, trapping heat in the atmosphere and impeding the flow back to space. The more CO2 in our atmosphere, the higher the surface temperature must be. The bad side of the greenhouse effect is being seen now. Modern industrial society depends on the energy extracted from burning fossil fuels. In effect, we are exploiting the energy-rich material created by photosynthesis tens of millions of years ago. Before the end of the present century, Earth's CO2 level is predicted to reach twice the value it had before the Industrial Revolution. The consequences of such an increase for Earth's surface and atmosphere and the creatures who live here are likely to be complex changes in climate and may be catastrophic for many species. Here we can see how the greenhouse effect works. Sunlight that penetrates to Earth's lower atmosphere and surface is re-radiated as infrared or heat radiation, which is then trapped by the greenhouse gases such as water vapor, methane, and CO2 in the atmosphere. The result is a higher surface temperature for our planet. Here we can see the increase in CO2 over time. As mentioned, scientists expect that the amount of CO2 will double its pre-industrial level before the end of the 21st century. Now that we have discussed the evolution of life on Earth, we are going to discuss the cosmic influences on the evolution of Earth. It is not possible that Earth escaped being struck by the interplanetary debris that has impacted the Moon. Our atmosphere makes the smaller pieces burn up before hitting the surface. However, this does nothing against larger pieces. Like the Moon, Earth was battered by debris. However, our geological activity covers this evidence up. Here we can see evidence of a crater on Earth, though it is heavily eroded. And here we can see an example of recent cosmic activity. In this desolate region, there was a remarkable explosion in the atmosphere about 8 kilometers above the surface. The shockwave flattened more than 1,000 square kilometers of forest and killed animals in an 80-kilometer radius. The blast wave even spread around the world, as recorded by instruments designed to measure changes in atmospheric pressure. Here we can see the best-known recent crater on Earth that was formed about 50,000 years ago in Arizona. The projectile in this case was a lump of iron about 40 meters in diameter, now called Meteor Crater. The infamous end of the dinosaurs was caused by a large impact 65 million years ago. This caused a mass extinction, where more than half of the species on our planet died out. The object that collided with Earth at the end of the Cretaceous period struck a shallow sea in what is now the Yucatan Peninsula of Mexico. Its mass must have been more than 1 trillion tons, determined by a study of a worldwide layer of sediment deposited from the dust cloud that enveloped the planet after its impact. Here we can see this infamous crater. As we can see, life and evolution is influenced by cosmic forces. Still, earlier in its history, Earth was subject to even larger impacts from the leftover debris of planet formation. We know that the Moon was struck repeatedly by objects larger than 100 kilometers in diameter, 1,000 times more massive than the object that wiped out most terrestrial life 65 million years ago. Earth must have experienced similar impacts during its first 700 million years of existence. Some of them were probably violent enough to strip the planet of most of its atmosphere and to boil away its oceans. Such events would sterilize the planet, destroying any life that had begun. Life may have formed and been wiped out several times before our own microbial ancestors took hold sometime about 4 billion years ago. The impacts by asteroids and comets that have had such major influence on life were not necessarily a thing of the past. In the full scope of planetary history, 65 million years ago was just yesterday. Earth actually orbits the Sun within a sort of cosmic shooting gallery. And although major impacts are rare, they are by no means over. Humanity could suffer the same fate as the dinosaurs, or lose a city to the much more frequent impacts. Beginning in the 1990s, a few astronomers began to analyze the cosmic impact hazard and to persuade the government to support a search for potentially hazardous asteroids. Several small but sophisticated wide-field telescopes are now used for this search, which is called the NASA Space Guard Survey. Already we know that there are currently no asteroids on a collision course with Earth that are as big, 10 to 15 kilometers, as the one that killed the dinosaurs. This Space Guard survey now concentrates on finding smaller potential impactors.